The Earth is a magnificent physical system. It's a great collection of atoms that are constantly changing, constantly reorganizing themselves as the globe itself undergoes change. Lecture 40 is the first of 3 lectures on the great geochemical cycles of the Earth, the cycles of earth, air, and water. And we'll see in this lecture that the Earth's store of water is essentially unchanging. The same molecules are recycled over and over again. I have 2 main objectives in this lecture. First, I want to introduce the general concept of Earth's geochemical cycles. Then, for most of this lecture, I'll consider the water cycle, a cycle that is essential to geological change and to life itself. Finally, I'll look at some of the ways that humans are altering this great cycle. The plate tectonics revolution has provided us with a new appreciation of the Earth as a remarkably dynamic planet. We see that new crust is being formed all the time along divergent plate boundaries, boundaries where volcanic material comes up and reaches the surface. We see that old crust is swallowed up all the time by subduction at convergent plate boundaries where old oceanic plate material plunges down beneath and into the mantle. And then we see as these great tectonic plates move from place to place about the globe, they cause earthquakes, they cause volcanoes, they cause the continents themselves to move. Indeed, these processes of plate tectonics are examples of the Earth's great cycles, which are the subject of these next 3 lectures. Every material object that we use, everything in our lives, every solid, every liquid, every gaseous substance comes from the Earth. Now that may be self-evident, but I want you to think about that in a little more detail. Wood comes from the Earth. Water, metals come from the Earth. Plastics, materials that we call all-natural, materials that we call man-made. These are all materials that are obtained from atoms from the same vast but finite source, the Earth. Now, to be sure, there are small amounts of material that come in as meteorites or maybe as comets. A small amount comes in each day. But that quantity is insignificant compared to the mass of the planet. For all intents and purposes, what you see is what you get. But the good news is that all of those atoms, that finite store of atoms, can be used over and over and over again. The Earth is the ultimate recycling machine. Every element, every compound on Earth can be described in terms of a geochemical cycle. Now, a geochemical cycle always involves 2 types of information. First of all, you need to have an accounting of all the different repositories, or what are known as reservoirs, of that element or that compound. Whether we're talking about the element gold, or water molecules, or the crust of the Earth, you have reservoirs. And second, then, you need to document the processes by which materials move from one reservoir to another. Well, let's give an example of this to make it more clear. And that would be, for example, the geochemical cycle of gold. Gold is element 79. Gold occurs commonly as the metal in which lots of atoms of the same element are bound together in nuggets or in grains or in other ways. Now, the major reservoirs of gold, remember that's the first thing you need to do for a geochemical cycle, include the oceans. It might surprise you that there are 50 kilograms per cubic kilometer. 50 kilograms of gold in every cubic kilometer of the ocean, dissolved. There's also lots of gold in hydrothermal fluids underneath the land. And this occurs, for example, when rocks are subducted, and hot water then circulates up and concentrates gold atoms in those hydrothermal solutions deep underground. We have lots of gold in metal ore bodies. That's where we go to mine gold. You have some gold that's concentrated in rocks and soils, especially in things called placer deposits, where these nuggets and these grains of gold get concentrated in stream beds. And of course, we have a huge amount of gold that's concentrated in reservoirs or repositories known as bank vaults, thanks to humans. There's several natural processes then that move gold from one repository to another. Water dissolves rocks and soils, and in the process, you have gold atoms taken up into water. You also have gold particles released and concentrated by fluid action into gravels, placer deposits. You have hydrothermal fluids, and some of the gold atoms that are taken up in hydrothermal fluids eventually end up in the ocean. Then you have miners, and miners transfer gold from the ore deposits into bank vaults, and those are all different ways that gold moves from one repository to another. As we've seen, human activities can affect these geochemical cycles, and that's a general phenomenon. Humans do, over time, affect geochemical cycles. And that's where we see in the gold cycle that humans extract the gold and redeposit it in other forms. Also, some of the gold jewelry that you wear that humans have recycled just naturally is a process of day-to-day use. The wear, for example, in a wedding band gradually gets smaller, gradually gets thinner. Gold atoms are returned to the environment from the human store. So the cycle keeps on going. The atoms never go away. They're just recycled over and over again from the various repositories. We'll find that new technologies may alter a geochemical cycle. For example, it's not yet economical to extract gold from the ocean, but maybe someday it will be. Maybe someday we'll find a way to extract gold atoms efficiently, and if so, then we'll alter the geochemical cycle of gold by that new technology. There are hundreds upon hundreds of individual geochemical cycles to study. We can study every single chemical element in its geochemical cycle. All kinds of small molecules can be studied. CO2, for example, carbon dioxide, or nitrogen gas could be studied. And all kinds of minerals have their own geochemical cycle as well. But in a very broad sense, there are three really important geochemical cycles. The primary cycles are the water cycle, the atmospheric cycle, and the rock cycle. And those will be the subjects of this and the next two lectures. Though quite different in detail, these cycles share four common characteristics. First, all of these cycles involve the movement of matter between reservoirs. Second, all of these cycles are driven by energy, either from the Earth's deep interior or from the sun. Third, all these cycles can be altered by human activities. And finally, all of these cycles are interrelated. They actually interact with each other. So now let's look at water. Water has played and continues to play a unique role in the geological and the biological history of planet Earth. Earth's water cycle, or the hydrological cycle as it's often called, deals with the reservoirs and the movement of water molecules, whether they're in the liquid state, the solid state, or their gaseous state. Now, Earth's water budget is almost completely closed. A small amount of water escapes each year through the atmosphere into space, a trivial amount just through gravitational escape, but a similar small amount of water probably comes into the Earth's atmosphere through the inclusion of comets. And we're talking about very small amounts, maybe the size of an Olympic swimming pool each year in terms of the total amount of water that's exchanged with space. And that's a trivial fraction compared to the Earth's total water budget. Now, I want you to also recall, though, there's the controversy about the small comets. This is the one raised by Professor Louis Frank of the University of Iowa, the idea that there may be a few small comets bombarding the Earth, and this could change our water budget calculations. That's still highly controversial. Keep reading the news, because maybe you'll see something more about it in the coming months or years. Well, depending on how you count reservoirs, there are perhaps 6 or 7 major repositories of water on Earth. And let me describe these. The accessible reservoirs, the ones where we can actually get water if we wanted to from technological means, include the oceans, then the ice caps and glaciers, that is frozen water. We have freshwater lakes and rivers. Then there's groundwater, that's water locked underground in vast interconnected reservoirs and channelways. Then the atmosphere, which contains some water. And finally, there's living organisms, which also have a stock of water. There is another repository which is not accessible to us, and that's hydrous minerals. These are minerals in which water molecules, or else just hydrogen protons, or OH, those hydroxyl groups, OH groups, actually are locked into the crystal structure. These are potentially vast but relatively inaccessible reservoirs of water. And indeed, these types of water repositories may be cycled down into the mantle, and so the mantle itself may hold vast amounts of water. Recall from the last lecture that subduction carries the lithosphere, the wet lithosphere of the ocean, down deep underneath a plate and then down into the mantle. So what you're doing is you're carrying wet rock down into the mantle. Therefore, you're carrying water molecules down into the mantle. If even a small fraction of this subducted water becomes locked into high-pressure minerals deep in the mantle, then it's very possible that the mantle, which is a huge volume, contains many times the total amount of surface water deep within the Earth, locked in. And it's also possible that this water cycles into the mantle and back out on the scale of a few 100 million years. It is even conceivable, although we don't know yet, that the entire oceans are replaced once every few 100 million years through mantle cycles. So that's part of the water cycle we just don't understand completely yet, but it's a fascinating one. By some recent estimates, all the water of the oceans could cycle in this quickly. Now, by far the largest reservoir of accessible water is the oceans. It holds now about 98% of all the accessible water at the Earth's surface. And you can understand why it's so large if you just look at a globe, see the distribution of oceans. Of course, we have the Atlantic, which is a vast ocean. But if you look at the other side, the Pacific Ocean is almost an entire hemisphere of water. So between 2/3 and 3/4 of the Earth's surface is covered by oceans, thus accounting for why the oceans can hold up to 98% of all Earth's water. By the way, the average depth of the ocean is now about 2 kilometers. So if you look at the surface area and think about 2 kilometers deep on average, that is a vast amount of water. Water is an excellent solvent. You recall that you can dissolve all sorts of ions into water, and this is why over billions of years the oceans have become salty. The principal elements in solution include sodium and chlorine, as well as calcium and magnesium. And of course, the ocean then becomes a very important part of the geochemical cycle of those elements. The second repository, glaciers and ice sheets, now contain an estimate 2% of Earth's accessible water. Most of the ice covers the Antarctic, the big land masses, and also Greenland. The rest occurs as very thin coverings, either of the polar oceans, the Arctic Ocean, or widely scattered in mountain glaciers and at high altitudes. As we'll see shortly, the distribution of water between oceans and ice reservoirs can change dramatically, and it has a very profound effect on world ecosystems, depending on the global climate. Third reservoir is fresh water on land, and that accounts for, at most, only about 0.4% of all the accessible water. Of this amount, more than 90%, by some estimates as much as 98%, is stored beneath the surface as groundwater. They're huge underground reservoirs that are formed by porous rock layers sandwiched between impervious layers. So this is not like a big volume of water that's continuous, but rather it's water that's sort of penetrated, seeped through the pores of various porous rocks. We also have lakes. We have rivers and streams. Though a major source of water for humans, it represents less than 0.04% of Earth's near-surface water. And then the atmosphere. The atmosphere holds only about 0.001% of all the water on Earth, and it's mostly in clouds. Now, even though this amount seems trivial, 0.001%, it's very significant because water cycles through the atmosphere so quickly. So the atmosphere can move very large quantities of water efficiently from one place to another. Part of the reason that the Earth's such a dynamic planet is that water is constantly moving. It moves from one reservoir to another by a number of means. Now, the hydrological cycle, like all cycles, features the complex movement, then, of water from one reservoir to another. We experience this cycle on different time scales. Part of the water cycle is experienced on a daily basis, just of weather, of raining, of evaporation off the ground, and so forth. But there are other parts of the cycle that take thousands of years or millions of years. So let's start with the oceans and thinking about the movement of water. The principal movement of water out of the oceans is through surface evaporation. So you evaporate water off the surface into the atmosphere. Since the salts in the water don't evaporate, the process then distills fresh water from the salt water of the ocean. Sun provides the energy for evaporation, which is especially rapid in the warm equatorial regions. Now, ocean waters are layered. The deeper layers are generally colder, they're generally saltier, they're denser. And only in the surface, the shallower layer in the surface, do you get most of the evaporation. So the deep water of the ocean is more or less locked in that layer, and so it's the surface layer of the ocean that sort of acts like a separate repository, a separate reservoir, isolated from the deep ocean. Ocean waters can move very large distances around the globe through currents. Now, they're surface currents that typically move warm water from the equatorial regions to the north, such as the Gulf Stream, which starts near the equator but moves all the way up to the north and keeps Great Britain and that part of Europe much, much warmer than it would be otherwise. After all, England is almost at the same latitude as Labrador, very far north. There are also deep currents that take the cooler water from the north and circulate it down deep within the oceans back down toward the equator. So in this way, the oceans play a very major role in redistributing the heat of the Earth. So now we have fresh water evaporating off the ocean surface. It's transferred then primarily by rain, but also by snow from the oceans to the land. And remember, even though that the atmosphere holds only 0.001% of the Earth's water, it transfers most of the water in these kinds of processes. The average residence time of water in the atmosphere is just a few days, so most of the rain falls back on the ocean, but a significant amount falls on the land, and this is how we stock our lakes, our rivers, our streams with water. Rain replenishes these repositories, and it may take hundreds of thousands of years then for that rainwater to circulate down and to fill a groundwater repository. So we have different time scales here. Rain falls quickly to fill the lakes, but then to fill the underground repositories is a much slower period of percolation, gradually the water easing its way down through these porous rock layers. Of course, that system of streams and river continuously pours fresh water back into the ocean, and the cycle continues. Ice caps and glaciers also participate in a very important way in the water cycle. You have snowfall adding to the net budget of ice and snow, and you have melting and sublimation, which helps take away the breakup of ice sheets, the formation of icebergs that then melt. All of this reduces the amount of ice, and there seems to be a balance at most period of time. These processes are slow on human timescales, but there can be major changes in the proportion of ice to oceans in geological history. And we sometimes can see changes that look rather significant. In 1998, for example, there was an ice raft the size of Rhode Island that broke off the Antarctic ice shelf. So we do see that's a pretty dramatic change. It doesn't change the percentages very much, but still we notice that over geological time you could have rather significant changes in the ratio of ice to ocean. In this regard, ice ages are particularly important. Ice ages represent part of the water cycle that spans millions of years. An ice age is a period of geological history when a relatively high percentage of the Earth's available water becomes locked into ice caps and into glaciers. The Earth's present ice caps began forming about 10 million years ago. For a long period prior to that, there were no permanent ice caps. The Earth was warmer. Now, the ice caps reached a maximum about 2 million years ago, and many times during the past 2 million years there have been extensive advances of ice from, for example, the polar north, covering North America and much of Europe. And then those ice sheets have retreated in a regular recurrent pattern. During the most recent glacial advance, which was about 20,000 years ago, sea level was hundreds of meters lower than it was today because there was less water in the ocean. The east coast of North America was 250 kilometers farther east, for example. There was a land bridge that connected Alaska and Siberia across what is now the Bering Sea. At the height of these glacial advances, as much as 5% of Earth's water can be locked in ice. So we see big changes can occur. We're now in a very brief period called an interglacial period. The present ice age may last millions of years more, so there may be more advances of ice, but we're in an age when the ice has retreated, and we expect at some point it may come back. Some scientists argue, however, that human activities, especially the extensive burning of fossil fuels, is causing, because it causes a buildup of carbon dioxide in the atmosphere, it may actually be causing a period of warming which could conceivably interrupt this large-scale cycling of glacial advance and retreat. If we warm up the Earth too much, the next cycle of advance is not going to happen quite so quickly or as easily. Plate motions probably explain the formation of ice caps 10 million years ago. And here's a key point. Thick ice caps can only form if you have a continent at a pole. If you have oceans at the pole, then you only form a relatively thin sheet of ice over the water. But with a continent, you can build up layer after layer of ice. It was about 10 million years ago that Antarctica really insinuated itself in that position across the pole and could start building up very thick layers of ice. And so it's possible that this influenced this global climate quite a bit. Also note that a lot of Eurasia and North America lie inside the Arctic Circle, so there is quite a bit of landmass. For example, Greenland and other parts of North America and Siberia that can also accumulate ice in a period of glacial advance. Why do you have periods of glacial advance? This is a real mystery, and it was a problem that was tackled by the Serbian civil engineer Milutin Milankovic, who lived early in this century. And his is a fascinating story. He was an engineer, Milankovic was. He designed reinforced concrete buildings. And the reason he came to study ice ages, which seems quite different than reinforced buildings, is quite amusing. He, like many of his countrymen, was caught up in nationalistic fervor. And one evening he was in a bar with a group of poet friends. They were celebrating the publication of a new collection of patriotic verses. There apparently was a wealthy banker at a table next to them, and he purchased 10 copies of this no poetry volume. So the friends began to celebrate with wine, it's said. After the first bottle, Milankovic writes in his journal, quote, "I looked back on my earlier achievements and found them narrow and limited." After 3 bottles of wine, he wrote that he had resolved to, quote, "grasp the entire universe and spread light to its farthest corners." Well, he did methodically set aside a few hours every day to study climate records. He even kept this schedule up as a prisoner of war during World War I. It turns out that a member of the Hungarian Academy of Sciences arranged for him to have a desk after he promised not to escape. Well, Milankovic explained periodic glacial advance and retreat as a result of orbital variations of the Earth. These cause a slight shift in the amount of solar radiation that reaches the northern and the southern hemispheres, and apparently then explains the glaciation. Here's what he said. There are 3 types of orbital variations that contribute to glacial cycles. They are, first, the eccentricity of the orbit, second, the precession of the axis of the Earth, and third, the tilt of the axis. And let's look at each of these 3 effects. The first and most major effect is a 100,000-year orbital cycle of changing eccentricity. Now, the Earth is now in a slightly eccentric orbit. It's elongated only about 1%. So at its farthest distance from the Sun in its orbit, it's only 1% farther than its closest approach. It's actually farther from the Sun in June and closer in December at this point. But the elongation of the Earth's axis is affected by the pull of other planets. And at times, in this 100,000-year cycle, it can be as much as 5% eccentric. That's much greater, so that the exaggeration between the closest and the most distant approach to the Sun is quite a bit more. So as the orbit becomes more elongated during the next 50,000 years, we're going to experience greater seasonal contrasts in the Sun's energy, and therefore greater contrasting temperature changes, colder winters, warmer summers in certain parts of the Earth. Okay, a second orbital variation. This results from the precession of the Earth's rotation axis every 23,000 years. Now, precession, you've seen if you ever have a toy top, and you see after it starts spinning for a while, it starts wobbling a little bit. And that wobble is called precession. The axis actually changes its orientation. Now, the average tilt remains 23 degrees, but the orientation with respect to the Sun changes. At present, it's the northern hemisphere that's tilted toward the Sun during the summer months, when the Sun is farther away. But recall, in 11,500 years, the tilt will have changed, so the northern hemisphere is tilting toward the Sun in the summer months. And that's when the Sun is close. So in this case, you're going to have greater contrast once again in climate. The net result is that the total amount of sunlight reaching the northern versus the southern hemisphere changes on a 23,000-year cycle. Now, the third effect is somewhat more subtle. It's a 41,000-year cycle of axial wobble. And in this case, the tilt changes from an average of 21.5 degrees to 24.5 degrees. And the greater the tilt, of course, the greater the seasonal contrast, because the more winter and summer contrast there is in the amount of sunlight falling on the poles. Now, taken together, these three effects, that is, the 100,000-year glaciation cycle with short-term 20,000 and 40,000-year glacial maxima, exactly match Milankovich's ideas about the various orbital variations of the Earth. The final point of this lecture has to do with the way that living things are part of the water cycle. Living things, including humans, require water to survive. Thus, while organisms hold only a trivial fraction of all the near-surface water, all life forms have to develop a strategy to obtain a reliable supply of water. It might surprise you to know that a human being requires 2 liters of water a day. The average person in an industrial society, however, uses directly or indirectly 6,000 liters per day. How can it be? You need 2 liters, but on average we consume 6,000. Well, we use perhaps several hundred liters per day in personal activities, washing and bathing and so forth. But most of the per capita usage has to do with irrigation for agriculture. And of course, industrial processes as well consume large amounts of water. The manufacture of paper, for example, consumes huge amounts of water as wood pulp is processed and transformed into white sheets. Agriculture particularly consumes water in arid parts of the country. If you've ever seen pictures of Palm Springs, it's a desert area, but there are farmers all around. There's wonderful, lush gardens. That's irrigation, and much of that water goes into irrigating the land, and of course it evaporates off. So we're using huge amounts of water to grow in these arid areas. As the human population grows, we're faced with important problems related to water use. First and foremost is the problem of water pollution. See, all water contains impurities because water is such an excellent solvent. But in many regions, tap water has contained large amounts of dangerous impurities, lead or arsenic, other dangerous substances. Some of these come from old pipes. Some of them just come from the fact that groundwater circulates through old chemical areas, and we just keep adding chemicals of these sorts to the environment as we throw away old batteries and old cars and other sorts of things. There's buried chemical waste everywhere. There's trash in great deposits, and as rain falls on those deposits, it picks up these impurities, carries them down into the ground. Gradually, that gets into our water supply. Now, rivers and lakes can be cleaned up relatively easily because the turnover rate in a river or a lake is relatively fast. But think about groundwater. It can take tens or hundreds of thousands of years to replace the water in a groundwater reservoir. If the water gets polluted when it goes into those reservoirs, it's a virtual impossibility to clean it out in any fast or efficient method. You just can't do it. So the pollution that we add to water today may be around to plague humanity for many thousands of years. A more immediate problem with the groundwater, though, is overuse. One of the largest groundwater reservoirs in the United States is the High Plains Aquifer that underlies a large portion of the Midwest. This reservoir now provides about 30% of all the water used for irrigation in the United States. The amount of water being withdrawn from this reservoir is much higher than the rate that it's refilling. You have to think of this as mining underground water. You have a huge reservoir, but if you're taking the water out faster, it's just like your own bank account. If you spend the money faster than you put it in, you're eventually going to run out. Consequently, the water level has dropped and the water yield is declining from this High Plains aquifer. And what do we do when that aquifer runs dry? Well, we're not going to run out of water. I can promise you that. We can always use desalinization of seawater, as they do in energy-rich Middle East. But what happens when the price of tap water goes up by a factor of 10? Because you suddenly have to use energy in a big way to obtain that water. I just want you to remember they were all part of this water cycle. Well, to summarize, every Earth cycle can be characterized by an account of all the reservoirs that hold that substance, and then a description of the processes by which the material moves from one repository to another. The water cycle beautifully illustrates these points. The major repositories include the oceans, ice caps, lakes and rivers, groundwater, the atmosphere. Water moves among these reservoirs in several ways: evaporation, precipitation, gravity making the water flow downhill. All of them are important in moving water from one place to another. And finally, living things, especially humans, may influence and alter the water cycle. In the next lecture, we'll look at another of the great Earth cycles, that of the atmosphere.